So this is the code of the course. It's going to be 6 lectures, 2 hours plus an additional hour, except today, because it's the first time there are no exercises, to discuss about the solution of the exercise I'll be giving you this week starting today. So there will be 5 exercise sessions and 6 lectures. This is going to be our Bible for the next 6 weeks. This is one of the nicest books on the topic. The topic is meanwhile not so young anymore. It kind of exploded in the 70s and in the 80s. Now it's kind of going down a little bit because, you know, in science, like in anything else, there are fashions. There are things who become popular and things that were popular, and then inevitably, after you find the main things, the main concepts then die out, like everything else. You know, it's life. So I will try to tell you why this thing was so nice, so long, what it has to do with a number of phenomena happening everywhere in engineering, in biology, in chemistry. This book gives plenty of examples, and we'll go through many of them, just to show direct application of these concepts. Then you can see that this, what looks like an abstract mathematical concept, instead has a direct formulation, a direct application to specific phenomena which are very important in many different fields. Like, for instance, the stability of bridges, where you just can walk or even drive through. Bifurcations are very important. The creation, destruction of fixed points, which are equilibrium points, as we're going to see, because you're going to see them today for the first time. Stephen Strogas at Cornell, very nice guy, great teacher, and this book is really fantastic. So we'll be going through the chapters, the first chapters of this. Of course, the course is too short to be able to go until the end of it, but I hope that after this, maybe you can make the extra effort of completing the book on your own at the end of this course, if you like, whatever we'll be discussing here. And these are more or less the 6 sessions that I thought to plan for this course, which is very similar to what I did last year, which was the first time. So essentially, not exactly, but essentially, each of these chapters, each of these sessions, each of this lecture corresponds to a book chapter. In some cases, the chapters are short. You can compact 2 of them in once. In some cases, the chapter is long. It's not even sufficient a single lecture to go through that, like in the case of the phase plane, which is very important because most of our examples will come from there. So flows on the line is today's show, after a historical introduction of the concepts. Bifurcation is a fundamental concept in this business. Bifurcations is the process that leads to major changes in the phase plane, so in the existence, creation, destruction of fixed points or equilibrium points by changing parameters of your dynamic system. Parameters that you find in the equation. So you change them a little bit, and then you can see that pairs of points can merge and annihilate, then they disappear, they're not there anymore, or some others will appear. And these points are very important because these are attractors for the dynamics. It means that the system will converge to them. So if the points disappear suddenly, there will be nowhere where they can converge. If they appear instead, there will be points where they can converge. And these points could be, for instance, like the crash of a bridge, like unstable equilibrium. And then, so next time, bifurcation. So we go through that, starting from one-dimensional systems, and then linear systems in 2 dimensions, phase plane, limit cycles, and Lorentz equations, and one-dimensional maps. The way things are structured, since it's very important to go through the main concepts, unfortunately, these last 2 things, which are in a sense the 2 main things of the whole chaotic business, will be a little sacrifice. So we'll try to go a little bit fast so that we can somehow discuss this a little bit in depth, more than I did last year. But one way to do it is somehow to shift some of the examples I'll be giving in the class, the ones which are not strictly necessary to understand everything, to the exercise session. So in the exercise session, there may be 15, 20 minutes that I can use to discuss a little bit about the examples before we go, or after we went through the solution of the exercises. For the exercise, of course, you can hand over your solution here before I start the lecture, the week after that. So for instance, for this week's exercise, that you already find at the end of this, but in a separate file already on the website of the course, I would expect them to be delivered before I start talking next time, next Wednesday at 9. But you can also send me a PDF. In fact, it's the way I prefer, because I assume that all of you can use an editor on your computer, generate, the worst case, a text file. But in this case, since there may be figures that you want to draw, it's very good, actually. It's a good exercise for you. And next time, we'll be starting a discussion about this on how to create phase spaces, how to construct on a computer, since most of these systems are not analytically solvable, and that's actually the principle of it. We'll try to find a description, a qualitative description of the behavior, the main feature of the behavior of the system, the asymptotic behavior, what is the final state of the system after a sufficiently long time, without actually solving the equations of motion. This is the whole business of dynamics. And we'll do it in 1 dimension, in 2 dimensions, in 3 dimensions, all the way up to the Lorentz equations. So you can send me a PDF, it's just the same. In fact, it's even better for me. But please don't do like last year people did, because of course this is one of the disciplines in which you can still use pen or pencils and a piece of paper, which is great, because nowadays, especially for instance, people doing our job, mostly computational scientists who do everything on a computer, almost forgot how to even handle a pen. So this is bad, of course, because it's very important to remember how to hold the pen, at least for signing documents, or checks. But I really prefer to use a text editor in this case, because then it would be more readable for me, and a good exercise for you to try to create a scientific document, minimal scientific document with the solution of the exercise I give. Okay, guys, I think that most of you have seen these objects here. We won't be dealing directly with fractals until the end of the course. Some of the objects we'll see, and most importantly, this is a fractal. This is a famous Lorentz attractor. This is the final state of a point subjected to the Lorentz equations in 3-dimensional space. So the point moves, winds a little bit here, and then it moves to the other side. It does the same thing, and then it moves to the other side. But these lines will never intersect, because this would violate the theorem of uniqueness, of existence and uniqueness of solutions of dynamic, of equations, of solutions of this, or the equations we'll be dealing with these dynamic equations, as you will see today. So, this is the Mandelbrot fractal. Fractals are objects which are self-similar at any scale. So they reveal the same type of pattern, the same type of shape at any level of resolution you can go. This is a classical example, and this is also a fractal. It looks like a surface, but it's not a surface. There are many more points than you can have in a surface. The fractal dimension in this case is slightly higher than 2, but we'll go to that, of course. So fractal encounters are part of dynamics. So the subject that deals with the systems evolving in time. This is what we'll be doing. We'll have an equation of motions, whatever it is. It can be a point or of laser, could be photons, could be chemical reactions, everything. Everything can be formulated in equations, and then we'll try to solve these equations without really solving, without really integrating the equation itself. A dynamic system may do a number of things, and we go through all these things, starting from the very simple case of 1-dimensional motion, motion on a line, flow on a line, which we'll be starting today, all the way to this 2-dimensional motion, 3-dimensional motion. So a dynamic system may reach a steady state, can converge to a point, or go to infinity, asymptotically. So it would take an infinitely long time to get there, even to the single point, if it is an equilibrium point. It can reach a periodic orbit, what in nonlinear dynamics is called a limit cycle, because in linear systems, we make a difference between linear systems. Here we'll be dealing with nonlinear system. I think it's clearly indicated in the title, nonlinear dynamics. In linear systems, as you know, there are oscillations, which are steady oscillations, like the one of a pendulum, for instance. There's the small oscillations of a pendulum, but also of a mass spring. The mass attached to a spring, then you pull the spring, and then the thing goes. If there is no friction, then it will keep going forever. Of course, you can introduce a friction term, then you don't have any more periodic oscillation. However, in nonlinear systems, you don't really have periodic oscillations except asymptotically. So the system may converge to a closed orbit, which is called a limit cycle, which, however, will be only approached asymptotically, only if you wait an infinitely long time. So this will be seeing this about the end of the course, and limit cycles start to appear in 2-dimensional nonlinear systems. Starting from 3 and higher dimensions, you may see something which is not a limit cycle, which is a so-called strange attractor, like in the case of the Lorentz equation. The point may converge, so your subject of the interaction may converge to a structure which is not really a surface or a point or a cycle. It's something else, and we'll see what it is. You can have chaos, cannot have strange attractors in less than 3 dimensions. So remember that at least. As well as you cannot have oscillations in less than 2 dimensions. You must have at least 2 dimensions in order to have a limit cycle, a cycle, sorry, a regular periodic oscillations. So dynamic systems occur in classical mechanics, in chemical kinetics, population biology. Will be taking examples from all of these different disciplines to clarify concepts. Little bit of history. I think that you know this guy. We owe him a lot. Pretty much the beginning of modern science. Because this guy had a big problem in front of him. We all had big problems in front of him. And he found not only could formulate precisely the question, but he also formulated the equation of motions, equations of dynamics, just to set up any possible problem of that kind. He was more interested, of course, in the motion of celestial bodies, planets, and the force that he had to put inside that equation. So he discovered the gravitation, and even the computational techniques to solve these equations, because he discovered calculus. So he did really the whole package. It looks so simple, but it's such a truly amazing achievement for a single guy to do that. So as soon as these equations were finally written, the first thing to do was to solving the two-body problem. The motion of the Earth around the Sun, or if you want, the motion of, if you have 2 mass points, different masses, doesn't matter, subjected only to gravitation, gravitational force, then you can solve exactly this equation. And you find out that then the motion is on a plane, and that both spin around the center of mass and so on, everything which is known. But of course, as usual, you start doing something, then people try to make it more complicated. There is not only the Earth and the Sun in our solar system, I would say in our galaxy. There are many more bodies. So what happens if you move from 2 to 3 bodies? This was done almost immediately. And people were confident, okay, now we are smarter, we know how to solve the two-body problem, we know more techniques and so on, while we were progressing, in science. So, should be able to solve this problem. However, until today, nobody really solved the 3-body problem. And in fact, Poincaré made really very important contributions in that. He reformulated these type of problems, particularly 3-body problems in terms of stability. He was asking what happens, is the solar system really stable? Is this system compatible with the possibility that, for instance, the Earth will fly off the system and reach some other solar system and so on? Is this a possibility contemplated in the equation? Then introduce the famous Poincaré maps, and we'll be going through that too. So one of the inventors of dynamics, what is now called dynamics. But he was also the first one to conceive the idea of chaos, to realize that even this very simple system with 3 bodies was very sensitive to initial condition, to where you exactly place this body at the beginning of the motion, or to the exact velocity you're giving to that. So being equations of second order, equations of dynamics, you need 2 numbers to start the whole thing. You need the position, the initial position, and the initial velocity of the particle. If you don't, of course, whatever I do, if you use a computer, but even a super powerful computer, any number will have, a finite extension. Will not have infinite figures. This is an approximation that your computer is forced to introduce, because it can only deal with finite numbers, no matter how precise. But this indetermination, which is generally different from one computer to the next, can lead to very different results for the dynamics on the long term, if the system is chaotic. And this is an intuition that already Poincaré had. Then, of course, the first half of the 20th century witnessed the creation and the massive applications of a number of nonlinear systems, like nonlinear oscillators, the invention of the radio, of the radar, laser. All these are, or include, nonlinear oscillation, with all that this involves. And most of these nonlinear systems were not really exactly solvable. Like in the good old times, you can just solve the two-body problem, you come up with the formula, and look very good. You did the best possible job. you can do that. But at the same time, fortunately, these pocketable computers, I mean, this is a room, so you couldn't really put it in your pocket, and your smartphone today is far, far more powerful than any of these beasts of the 50s. These instruments allow the solution, the numerical solution, the first numerical solutions of these very complicated nonlinear systems. And almost immediately after that, Lorentz, in 1963, using one of these machines, tried to solve his equations of motion for masses of air in the atmosphere, because he was a meteorologist. So he wanted to find a motion, describe the motion of, airs to make good air masses in order to make good weather forecasts, to understand this convection. Convection rolls in the atmosphere is a very complex system, and he realized that the asymptotic solution of his equations was this one. This is a section actually in 2 dimension of the Lorentz attractor. And even if it was the 60s and the guy was not really a mathematician or a physicist, but at the time people knew a little bit of everything, he understood that this was not a simple surface or sunset at the end was somehow closed in itself. It was something else. He called it an infinite complex of surfaces. Now we call this a fractal. A fractal is an infinite complex of surfaces. It's much more than a surface. There's many more points, infinitely many more points than you can find on a single surface. So it's something which lies between a surface and a volume. In fact, this fractal dimension is between 2 and 3, as we're going to see. In the case of the Lorentz attractor, in fact, it's very close to 2, so it's almost a surface. That's why it looks almost bidimensional here. So, and of course, he realized by solving the equations again, by starting with slightly different initial conditions, how variable, so the fact that 2 points starting really almost at the same point initially with their motion, if you keep going on in time, they will at the end follow totally different trajectories. They will be then very far apart in a way that you cannot apparently predict. Although the system is deterministic, there is no stochastic factor here, except of course the fact that you have to deal with finite numbers because you're using a computer, right? So you don't really. So the system is deterministic, and yet it seems that you cannot predict its future evolution because the slightest indetermination in the initial condition will generate a lot of noise, a lot of indetermination in the future evolution of the system. This is what is called the butterfly effect. When they say that the flapping of a butterfly in São Paulo can generate a hurricane in Miami or something, which is of course not exactly like that, but this gives the idea that a very small thing can really generate very different evolution of the system, in this case a different weather forecast. Which also explains why until today, despite the fact that we have super powerful computers and very refined models, weather forecast is not very reliable a few days after now, because so many things can change, so many small things can play a role in that and change completely the forecast. Can go from heavy rain to sunny day, which is at the end what people are interested in knowing. The Lorentz attractor is a fractal. Progressing in history, in the 70s, there was a golden age of chaos, mostly for 2 reasons. In fact, of course, there were some initial applications of the chaos theory, or somehow to see that turbulence, which is, it's a very, very complex phenomenon, very, very difficult thing to understand. But Ruel and Takens introduced a theory using strange attractors for turbulence. So they tried to use some of the, somehow this concept, although there was no real theory somehow at that point. What was known was essentially what Lorentz did, and a little more than that. Things changed and accelerated considerably when in 1976 Lord Robert May introduced the logistic map in a review paper that he wrote. It was a very simple map that he took from population dynamics. So because he's a mathematical biologist, it's a very nice book. It would be nice to see what happens if you do that and if you iterate the map. Then he found very complex things. That there were some intervals in which basically at the end the point of the map was not really converging to anything, to any set of single points, but to a really a huge variety of possible final states, which were not really final states because it would be somehow jumping from one to the other one in another strange attractor, in another fractal, which is a fractal of the logistic map. And right after that, studying still, I mean, motivated by this, Mitchell-Feigenbaum, whom I met actually a few times, discovered the universality of one-dimensional maps. He showed that the behavior of the logistic map was no different than the behavior of any one-dimensional map under some conditions. So, which established a link between chaos and critical phenomena, which was very popular at the time. The theory of critical phenomena in statistical physics, understanding essentially phase transitions, water, gas, so liquid gas, or ferromagnetic, paramagnetic transitions in iron, in magnets. And then in the 80s, after this, there has been experimental verification, and chaotic behavior has been found in many different situations, in fluids, chemical reactions, electronic circuits, mechanical oscillators, semiconductors, you name it. All works done mostly by these people, but of course by many others. These are the most famous names. So this is a very short, very essential history of that. We won't go, of course, through the details of this, but of course we try to touch the main things so that you can have a close enough view of what nonlinear dynamics and chaos is all about. And this is, again, a more complete history, starting from Newton solving the two-body problem until Poincaré attempting to solve the three-body problem unsuccessfully and conceiving the first idea of chaos. And then, these nonlinear oscillators, then the computers, the Lorentz equations, turbulence, the logistic map, the universality by Feigenbaum, and then the more recent works on applications of chaos, but also, solution of more involved nonlinear systems, which, pop up in many different sectors of life and science. Until the 80s, it became really a very fashionable topic, and there were many, many papers written on this. Sometimes it's enough just to change a parameter in something to get something interesting. Sometimes it's just, a cheap way to get a new paper. You can look at this both ways. But it is science, all right? Okay, so after this brief historical introduction, which didn't really have anything deep in it, we can start to go a little bit into the concepts. First of all, we will be dealing essentially with two types of dynamics, mostly with differential equations. So we try to solve some sort of equations of motions all the time without really solving the equations. In some cases, we'll do it just to see whether the exact behavior of the real solution of the system matches what we are able to infer about the dynamic behavior of the system from geometric arguments. So the geometric approach of nonlinear dynamics. So it's evolution in continuous time. At any time step, you try to understand where the particle is, what is its velocity, where it's going. This is the first type of system, by far the widest class of system that we'll be dealing with here, until, hopefully, in the last lecture of the course, in 5 weeks, we'll deal also with iterated maps, especially with the logistic map, which is a different type of process in which basically you transform, you go from in a discrete way from one position to another one by applying a transformation on the initial position. So you know where the particle is now, you put it in the equation, you get a new position, which is some jump away from the first one, and so on, until you see where, by repeating continuously this operation, where this point is going. So in this case, the evolution is in discrete time. 1, 2, 3, and so on, each time corresponding to one iteration of the equation, of the map. This is a classic equation, right? This is the damped harmonic oscillator. Damped is not a bad word. It's not damped or something. Right? Damped harmonic oscillator. So, of course, being a dynamic equation has to be second order. This is the mass, classical Newton equation, and the force that you see here on the first side of the equation as the classical spring term, kx, which is, of course, goes linearly with the displacement of the spring from the equilibrium position. And there is also a friction term, which breaks the motion. So it's like doing actually, it's like a real oscillator, because if you try to do the same thing with the mass, there is always the air, or the thing can somehow slide over a surface, you always have this friction term in there. In order to deal with this system, if you can estimate this B, and of course if you know the mass of your body and the constant of the spring, then you can solve this system. You know, this is a very well-known system. So these are the types of systems that we try to solve. Of course, in some cases, the solution is exact. This is an ordinary equation. There is only one variable, which is the position, because it's in one dimension. You know, if you're thinking about a spring, the object moves only on a line. It can move to the right, to the left. In this case, in fact, it does oscillate. It doesn't make a complete oscillation because of damping. So these are damped oscillation, means that at the end, the oscillations will become smaller and smaller until the body converges to an equilibrium position after sufficient time has elapsed. But there are other examples too. This is the heat equation, very famous equation. Mathematical physics, many other environments, the fusion equation. What's the difference here? U, in this case, tells you basically what is the energy at a given position in space at a given time. So it can be a function of 4 variables, 3 space coordinates and time. This is why you have partial derivatives, because you're deriving only with respect to one of the many variables the function depends on. The good news for you is that we won't be dealing with this, which is of course a far more complex situation, and you won't be seeing much about this in the book either, even if you go to the latest chapters. But of course, these are very important systems too. Our focus will be on ordinary differential equations like the one that you see in the previous slide. And in general, we'll be dealing with this type of situation here. So we have a first derivative of a variable, which can be the position, but not necessarily, as we're going to see. And then there is a function of all the variables. So if you have n variables, x1, x2, xn, these functions here to the right-hand side, on the right-hand side, will be usually smooth functions. Otherwise, you have pathological situations that we're going to see. So it must satisfy the theorem of existence and uniqueness of the solution. But for that, there are wide conditions. The function is smooth enough, like most functions that you see in nature, then it's okay. And then you have, of course, as many equations as there are variables here in order to have a complete system that you can, in principle, solve. Okay, so this x dot, of course, xi dot is just a derivative with respect to time. These variables depend only on time. Okay? So that's why they are ordinary differential equations, because there is only the dependence on one variable. So the derivative is the total derivative if you want, because there is only one variable that depends on. If you have, however, higher order systems, because all dynamic equations are second order systems, because that's what Newton discovered, right, in his Principia, because there is mass times acceleration is equal to a force. Acceleration is the second derivative of the position, right? The velocity is the first derivative. The acceleration is the derivative of the velocity. So what happens if we have, because after all, we want to deal with real systems, real equations, right? So what happens if we have then a second order equation, like for instance the one that you've seen before for the damped harmonic oscillator? We can use a trick and turn this system into a first order system with 2 variables by introducing an intermediate variable, which is the velocity. So the first variable, x1, is just a position like before, but that wouldn't be much of a progress if you just replace x with x1. It would be just the same equation. But the derivative of x1 dot becomes a new variable, x2. It looks like, like a baby trick. But it's useful, because if I do that, now the first derivative of the new variable x2 is the second derivative of x1, which is the second derivative of x, which is this. This is the second derivative of x. And therefore, what I get is, if I bring everything to the second side, minus b divided by m times the first derivative minus k divided by m times x. So, but since x dot is x2, right, the first derivative of x is this new variable x2, then I get this equation here, which together with that forms my new system, which is this one now. So what was a second-order system in one variable, describing in this case the motion of a spring, of a mass subjected to a spring force plus some friction term, became a first-order system in two variables, x1 and x2. We'll be doing this all the time. Whenever you see a second-order equation, which is, like I said, is the equation that you see all the time, because this comes from the Newtonian dynamics, which is until today, 2013, still valid. In some cases, you can make approximations so that the equations you're studying is not really the dynamics of mass points, so it can be formulated directly as a first-order system. But if it's not, we can always do this trick and turn the system into, like you've seen before, x1 dot, x2 dot, x3 dot, and so on, as a function of the individual variables, x2, x1, or combinations of both. Now, this is still a linear system. You see, there is no other power of the variables here which is not 1. This is the easy case, although they may be linear, because linear systems offer a number of advantages and many approaches that you can use to solve them. Fourier transformation, Laplace transformation, normal modes, very nice tricks. For nonlinear systems, you don't have these things. This is why we're here. Otherwise, we could invest our time in a more constructive way. The system is linear. And life is not only simple. This is not a linear system. Why, by the way? Why is this not a linear system? What's the thing that makes you think that this is not a linear system? Of course, I'm talking to the junior guys here, right? Because there are people with some more experience. So why is this not a linear system? What is the thing that makes it different from the case you've seen before? So this is, again, a second-order system. You see it, of course, because this is the equation of a pendulum, swinging. What's the thing? Yes, I don't have time, yeah? So I have to finish by 10, by 11. So let's go. So what is the thing why this is not a linear system? The variables are, the variable in this case is only one, is x. Then, of course, since it's a second-order system, I can make a transformation like before and turn it into a first-order system in two variables, right? If it's linear, it means that all these variables are present with power 1. If it's non-linear, it means that this is not true. So by looking at this equation, I know that this is not a linear system. Why? Because, so what is the thing? Of course, this is normal, okay? G and L are constants. This is 0. This is a equality, and plus, of course, plus and equal, we know. So I guess that perhaps the reason is that there is this sinus here. Because the sinus is a nonlinear function of x. Unless x is very small, then it can be approximated as x. This would be the so-called limit of small oscillations of a pendulum. The only case that you study in basic physics books when you're young. Because the real system is this. This is the full equation of the pendulum. This accounts for the fact that you can kick your pendulum so hardly that it can even swirl over the top. Right, you push it, and then it swirls over the top. Whereas the limit of small oscillations is when you move it a little bit, and then it just does this. In that case, you can approximate the sinus with x. But if you want to turn this into a first-order system, you have to do the same trick as I said before. So introduce variables x1 and x2, where x2 is a derivative of x1. And then that's what you get. So this is now a first-order system. There are only first derivatives, so two variables, which are the position and the velocity of the pendulum. These are the two variables I need to determine the future evolution of the system. Like in any other second-order system, right? Any equation of motion according to Newton, you have two variables that you have to determine in order to be sure that the future is established forever. So you can determine the future motion at any time, and even the past motion, in fact. So the analytical solution of this is very difficult, but there is an analytic solution by using Jacobi elliptic functions. This is a well-known thing. It's a difficult exercise, but it's a nice exercise. So you know exactly how to solve this. But we don't care about that. We'll try to have a hint about what really happens in this system without solving the system. by using geometric approach, which is what I hope you will be learning starting from today, if you are not familiar with that. So, like I said, the simple case of linear, so of small oscillations, when you have, the pendulum just swinging a little bit, not very much, is when, of course, the sinus, so if x is small, if the displacement with respect to the equilibrium position, which is, so this is your pendulum, this is the equilibrium position, and this is x. All right? So if this x is small, then the sinus of x can be approximated by x, because I don't say that, this is a Taylor expansion of the function, a trigonometric function. So you must be familiar with these things, right? Because this is basic math. And this is the limit that people study in basic physics books, even when you're young, because in this point, in this case, somehow the system becomes linear and it's trivially solvable. Then you get a simple oscillation. Just like for the mass spring. It's the same thing, just goes back and forth with some period which depends, of course, on that. It doesn't depend on the mass. You see, there is no dependence on the mass here. It doesn't depend on how heavy your pendulum is. The period of the oscillation for the small oscillation limit depends only on the acceleration, gravitational acceleration on the ground, and the length of the pendulum. So this is one of the first things that was realized when the first pendula were analyzed. However, if you move your things a little bit more, so that it starts, oscillating more wildly, up to the point that it even makes this equation cannot tell you what happens, because the approximation will be violated. Sinus is not x. Sinus is x only when x is small. So what happens in that case? What kind of forecast can you make? We try to solve equations this way. In some cases there will be approximation which will let us understand things. In some cases there are not such approximation, and we try to understand things anyway. What we have in general, like in this case, two-dimensional system, first order two-dimensional system, we have what is called a phase plane. The two variables can be displaced here, represented, so x1 on the x-axis and x2 on the y-axis. Each point here represents position and velocity then of the original particle. Or if you want, in the language of the first order system, x1 and x2 at time 0, which can be t0, but let's say it's 0, it's the same thing. And then you see how this thing progresses. So this will be a trajectory of the system, because at each time, the position of the point here will tell you what is the position of the original particle and its velocity. That's all you need, this the description of the motion. So with a computer, you can compute by solving a question like this with the so-called Runge-Kutta method, which is the one that everybody uses. It's a fourth order method discussed next week. It would be nice to see some of these things in the assignments I give you, because it would be nice if you can, of course, apply the theory and understand the motion, and then, of course, compute the real trajectory and see whether your forecast is confirmed by the actual evolution of motion when you solve the equations. Because you can always solve equations numerically, fortunately, because otherwise you'll be bounded by the theory. In some cases, you cannot really solve equations analytically. In many cases, actually, for the most interesting systems, you can't. Therefore, it's compulsory to solve them numerically. And then it's all a kitchen. You need to know how to do it. You need to control the approximation you do it, because it's not an exact solution, blah, blah, blah. But you can get good results. At the level of this course, for the exercises I'll be giving you, you can usually do a very good job. I mean, if you understand how to program this. But it's a very nice thing. I mean, it's a few lines of code to compute the motion, to solve, for instance, for the Runge-Kutta method, these equations of motion. So if we have a one-dimensional motion, like in this case, one variable, you have a two-dimensional phase plane, because you have the position on one axis and its velocity on the other axis. If you have two-dimensional motions, then you have 4 dimensions, because you have 2 positions and their corresponding velocities. If you have n variables, you have a 2n phase plane. because you have n positions and n velocities. We'll be seeing mostly systems of this kind, because at least, in a two-dimensional plane, we can better see what happens. But there will be enough to understand things, well, except in the case when you go 3 dimensions, because then you really have chaos, and you can only see it in 3 dimensions. But in most of the cases, we'll be here. Now, the phase space is completely full of trajectories, because you can always use any point of this space as initial condition. You can say, what happens if I'm here? Then I solve the equations, and then I get a trajectory. If I'm here, trajectory, here, trajectory, and so on. That, of course, if your system is sufficiently well behaved, if there are no forbidden values of the position of the velocities, which you may have in some cases. But in general, there won't be situations like this, and you can be pretty much everywhere on this space. Once you are at any given point, you can apply the equations of motion and get your trajectory. And that's pretty much what we want to do. Given the system, we want to draw the trajectories without solving the equations. That's interesting. It looks like magic, but it's not magic because there are a few things that we can learn that make this task possible. In some cases, even easy, but in most cases, it's not easy. But there are theorems we will be seeing, a number of tools we can use. Now, can we handle explicit time-dependent equations? This is the forced harmonic oscillator. Looks like the one before, right? But there is this additional force coming from the outside. No? It's like when you are with your hand also pushing your body attached to the spring and try to make a difference. It's a periodic force because of this cosinus. So it tends to follow the oscillation. And it's time dependent. Now, in this case, you can do this trick here. You can use the usual thing that the velocity becomes a variable. Bless you. So the second variable is the velocity. But then you can also set as a third variable time explicitly. So x3 becomes t. By doing that, then you won't be treating time as an independent variable, as you usually do. You will be treating it as a new variable, which depends, of course, which is the same dignity, the same role as the other two variables. But we won't be doing this very often. The important thing in this case is the fact that this is an effective 3-dimensional system, because it's not enough to specify position and velocity of the particle. You also need to specify the time where you are, because the time where you are changes this thing of the equation. You can be at the exact same position with the exact same velocity, but if time is different, then the force acting on that thing will be different, and that generates different trajectories. So you need to specify 3 numbers. That's why you have a 3-dimensional system. Did it just for the book. Then, of course, we won't be doing that. We won't have an explicit dependence of time in our equations. It's kind of a little tricky. And in this case, of course, by doing this thing, effectively you get rid of the explicit time dependence. So, okay, this is what I told you. So then, why are nonlinear systems so hard to solve? So basically, why are we all here? Because it's and get things as complex as chaos or limit cycles. What is the good thing about linear systems? But the good thing about linear systems is that you can split them in parts. The effect of the sum is the sum of the effects. And you can use a number of techniques that simplify the solution, like the Fourier analysis, the Laplace transformation, normal modes. Nonlinear systems are not like that. In the example that Strogas puts in his book, if you listen to your 2 favorite songs at the same time, you don't get twice the pleasure of listening first to one and then to the other one. You get just noise. So this, if you want, simple instance of a nonlinear system. It's a very nice example. On top of that, nonlinearity is everywhere. So we can simply just put it under the rug because it's complex. Lasers, turbulence, superconductivity of Josephson junctions, and a number of other examples are full of nonlinearity. They couldn't be there if not because of nonlinearity. So we need to, face that, try to solve it. So this is basically the diagram that ends the first chapter of the book. On this axis, you see how many variables you have. On this axis, how nonlinear the system is. So here it means few variables linear systems. Here means many variables nonlinear system. And in fact, here you have the most complex situations. The equations of Einstein for general relativity, earthquakes. So the variables now, for instance, in this case, are the points in space, right? Because each point in space has some properties, like in all field theories. Field theory means that each position in space is a property, like for instance, how strong the electromagnetic field is. And it's a continuum of variables, because each position has characterized by specific values, of course, varying continuously. But then depending on the system, like for instance, in this case, if you want to know how the geometry is curved by masses, then you have the nonlinear equations, the Einstein's equations, which, they're highly non-trivial. They look very nice, very compact form, but they're very difficult. But other things like fibrillation or earthquakes, also in earthquakes, each point on Earth has its own seismicity, its intensity of the strength. But then, of course, it varies in a discontinuous way. That's why you have the earthquake. At some point, there are some extreme values of this stress that releases this energy. And then, the Earth cracks, and there may be accidents. But also lasers are here, Josephson arrays. And the difference between this and this is that in both cases you have infinite variables, but here you have a discrete infinity, so countable infinity. Like for instance, if you have a lattice or a crystal, then you have all the atoms. But you have infinitely many if you take any piece of material, because there are billions of atoms in there. So in the limit, you may be infinite. They are equally spaced, usually, because they are ordered in some sort of lattice. And each of them, of course, as a property, will have its own variables, which are coupled with the other variables. Then, of course, if you are in a linear situation, I mean, these are situations that are very, very familiar. People are mostly familiar with equilibrium statistical mechanics, molecular dynamics, solid-state physics, and the usual coupled harmonic oscillators. Of course, if you have, instead of having a single oscillator, you have infinitely many oscillators, all coupled to each other. This is still one linear system, but only the variables are infinite. But there could be nonlinear oscillators. We're going to see some of them. The van der Pol oscillator, for instance, is a nonlinear oscillator. And the lasers, non-equilibrium statistical mechanics, all these things. In this case, again, you have infinitely many variables, although each of them is separated by the other ones, say, an infinite population of things, but the system is nonlinear. So this is the frontier, because most of these systems have, of course, they have been studied for a long time, but one cannot really say that he has, a solution, an easy solution for all of these cases. Certainly not for the Navier-Stokes equation. As you know, it's one of the millennium problems. If somebody solves the Navier-Stokes equations or shows that it cannot be solved or something, then you get $1 million, right? Even today. So just to tell you how non-trivial these problems are. What we'll be doing, we'll start from here, one-dimensional motion, nonlinear, and then we'll move all the way here. We will not touch this area, so this is somehow to give you a good day. But of course, we insist a little bit on this, and at the end, we'll finally have both the iterated maps, the logistic map in particular, and the Lorentz equations to show you a concrete example of chaotic behavior in a continuum system. So this is basically what we'll be doing from here to here. So from the nonlinear part, from the smallest simple system where you have 1 degree of freedom, which is motion on a line, the guy can only move to the right and to the left, the 2-dimensional system, 3-dimensional system. And that's it, because that will be the end of October, basically. Okay, so that was supposed to be then the first thing to be discussed here, the simplest possible thing. This one, the first order system that I showed you before, can also consist only of one variable, like in this case. So the derivative of x is f of x, where f is any function of x. Of course, it must be a nonlinear function of x, otherwise, there is nothing to learn from it, right? Because if I have this equation here, By the way, what's your background? Because of course I know them. So are you what, engineers or mathematicians or physicists or what? What about you?
Signal processing, communications engineering.
I see. And you? You?
Just a fourth-year student.
Yeah, so physicist, yeah? And?
Electrical engineer. Physics also.
Computer science?
Computer science, okay. So I guess that all of you have solved equations like this before, right? Derivative is equal to x. So what's the solution of this equation? This is a linear equation, right? So basically it tells you that the growth, the velocity of the particle is coincides somehow in this case, because I didn't put any coefficient here, but I could put a coefficient lambda. But say also in this simple case in which lambda is 1, it just coincides with the position of the particle. Which means that the farther the particle goes, the faster it will be moving. So the motion is very, very fast. And in fact, what is the solution of this? Now you must answer, because I mean, this is, if you don't know this, I mean, or at least, if you are too shy, just write it on a piece of paper and then, we can discuss this confidentially. So what is the solution of this simple linear system? Derivative, first derivative now, equal to x. So, which function solves this? Sorry? Right, exactly. So, e to the power of t, because the variable is t, right? So if you derive this, in fact, what is the question by this equation? What is the function whose derivative is equal to the function itself? It's the exponential. It's the only variable, it's the only function whose derivative is exactly equal to that, because you can derive this infinite times and you still get e of t. That's why I spoke about very fast motion. Very good. So, and since you are brave enough to do this, this is your prize. I always carry some of them with me. Because I understand that you need some extra incentives. So this is what you get if you answer correctly questions that may be asked during the course. I have a few here, so there will be other questions. Okay, was it good? Oh, you know it, right? Actually, I get one myself because I think it's very good. And this is more or less. So this was the first time we had the small exercise at the beginning. But in general, I will probably make it like 5 minutes break. But if you can stay until, can you stay until 11? Yeah? Okay, so let's have a 5 minutes break then. Guys, let's try to carry on and try to learn something on top of the history and everything. So today we'll be discussing with this, and the exercises you will have to be solving next time, which are already online, are about these systems here. So one variable, of course, there is one independent variable, which is time. We want to know where this particle is going to be in the future, starting from any given point. F of x is a smooth real value function of x. Could be the sinus, like we've seen before. In fact, I think we just started with this example. Could be x squared, which is also nonlinear, or x to any power, which is not 1. And does not explicitly depend on time. We showed what happens. It may depend on time, then you turn the system into a two-dimensional system by setting time as a second auxiliary variable. But things get a little bit messed, so we won't be doing that. Although, of course, there are examples like this I showed you before. The example of the forced harmonic oscillator, in which you put this force, apply this force from the outside, which depends on time because it follows some oscillation. Okay, so this is the first example. Just, x dot equal to sinus of x is the simplest possible nonlinear system, except for x squared or something. Okay, nonlinear because the sinus is a nonlinear function of the argument x. The funny thing is that in this case, there is a simple exact solution. The equation can be solved exactly this way. You separate the variables, you integrate both terms. Integral of the t gives you the finite increment of time, so t minus t0, where t0 is the initial condition, the initial point of your motion. And here you have the integral from x0 to x, which is the position at time t, of this function here, which is well known. I find tables for this. It's very simple to do it, and you get this. So it's not obvious, but it's there. Of course, if you want to make the explicit dependence on time, you can use the exponential here, but the exponential of t minus t0 becomes then this argument, and then you derive the function of x. But as you see, it's not obvious what happens here, right? I mean, even intuitively, even if you derive these things. The exact solution is not transparent. So what happens if we go to infinite times? Can you really see it from here? Well, maybe, but it requires some sort of, tricks or some, manipulations on this equation, which is actually the real solution. It's the function that we're looking for. But in order to find out what happens to the point after a sufficient long time, I don't need to solve this equation. I can do this. So this would be my phase plane, so to speak, where x is here and the velocity x dot is on the y-axis. So you should get familiar with this kind of thing, because we'll see this all the time. X here, x dot here. If I plot how the velocity x dot changes in x, it's basically the sinus. So it's basically I have to just plot sinus of x. If the sinus is positive, like here, here, and here, the velocity is positive. So the point is moving to the right. Right? This is why you see these arrows here point to the right. If the point is anywhere here, then it moves to the right. On the other hand, if you are here or here, so if the point is anywhere in these areas where the velocity is negative, because the sinus is negative, then the motion points to the left. Okay? Because this tells you this is the velocity of your particle, your point. So if the velocity is positive, it means that at that time you are moving to the right. If it's negative, it means that you are moving to the left. And there is no other possibility, because the motion is only on one line here. You can only go to the right or to the left. If you are on the plane, it's more complex, because you have two components of the velocity and you can make different things. But here we are one-dimensional system, the simplest possible. Now, of course, the velocity can be 0 too, right? So if you are at a point in which the velocity is 0, of course, the system will stay there, because it doesn't move. It doesn't move to the right, it doesn't move to the left. This is called a stable point. A fixed point. It can be stable or unstable. We're going to see that. So you can already see here what is the difference between a stable and unstable point. The black dots here are stable because to the right and to the left of them, the motion points towards them. Here, for instance, at pi, if you are a little bit to the right, the velocity will be negative, so the point tends to go back to pi. Here, instead, if you are slightly to the left of pi, then the motion takes you to the right again, back to pi. Here, for instance, 0, or at 2 pi, or at minus 2 pi, the opposite happens. If you just deflect, if you're just a little bit outside of this point, then the velocity, so the system will take you away from there. That's why it's an unstable point. It's stable only if you are sitting exactly there. But if you deviate a little bit, then the field, the velocity field, will take you away from it. So we'll be seeing this all the time, stable and unstable points. We'll see also how we can compute them. So suppose that we start from here. This is pi fourth, because this is pi half, right, where you have the peak of the sinus when it's 1. Then you have here is pi fourth. So the motion starts there. So what do you expect to happen? So what is the velocity that I have here? The velocity is this one, right? It's written here, right? So velocity is this. So it's positive. So the motion will take me to the right. But the velocity increases too, all the way until I get the position pi half. And then it decelerates. It reduces until it gets to 0. So what kind of situation do I have here? this one here. So this is pi/4, and this is time. So this basically indicates your trajectory, so how really the position is changing in time. So first the motion is faster, you see here is concave up because the velocity is increasing. Then when you get to pi/2, the velocity starts to decrease again. Then you have that it becomes convex because it's decelerating. So when you have the situation in which the velocity peaks during the motion, you will see that there is an inflection point here. Because of course the second derivative will change here of the velocity, so the acceleration if you want. There will be a positive acceleration here because the velocity increases, and then there will be a negative acceleration or deceleration because the velocity decreases. That's why this is seen as a second derivative, so it's an inflection point when you have this change here. Eventually converges to pi, which will be reached asymptotically. So if a particle starts from here, it will get to pi in an infinite time. Very, very slowly. At some point, because of course, the approach to pi is very slow because the velocity is reducing. The closer you come to pi, the smaller the velocity is. And when you get finally to pi, infinite time, the velocity will be exactly 0 and will stay there. In fact, we will just get there. There is nothing that happens after infinity. Okay. This was a specific situation, but I can start the motion from any point I want. So what happens in those cases? So this is what I got before. Acceleration, deceleration. If I start from this part here, say in this case, this is 0 pi. If I start from, say here, any point here, here I have only deceleration. Because the velocity goes monotonically down. It never increases, all the way to 0. That's why you see the profile of the trajectory changes, because you can only, so it's just concave down because of this deceleration. So there is no inflection point, because there are no changes in the velocity, no changes in the sign of the acceleration. There is a systematic deceleration. For the same reason, if I go past pi, but before 3/2 of pi, so before this point here, say, I only have a deceleration to the left. That's why this thing is going down to pi again, because it's moving to pi here. The velocity is negative, so it brings me back to pi, that I will reach in an infinitely long time. Symmetrically, if I go past this point here, say, there will be first an acceleration towards the left, and then the deceleration, which is shown by this inflection point. Same as here. So the situation is, of course, totally symmetric. And of course, if you want to go to negative values, the function is periodical. You find exactly the same thing, the same scheme that you see here. So you see, I didn't solve the equation. I didn't take a look at what is the exact solution that you can get in this case. I just derived these results here, just from the velocity field, what is called the velocity field, which in this case is very simple, it's a sinus. Of course, if the particle starts at a point where the velocity is 0, like in this case, pi, the velocity is 0, and you see the particle will stay there forever. That's why you have a flat thing. At any time, it always stays at pi, because the velocity is 0, so it stays there. It's comfortable there. Now, fixed points and stability. General procedure, I draw the graph of fx. So like in this case, this is what we did for the sinus, right? This was the sinus before. And then I check the intersections, and I draw the velocity fields. Here we are below 0. The velocity is negative, so the arrow points to the left. Here is positive to the right, and here is positive again to the right. So then by taking a look at these fixed points, you see that this one is attractive because the velocity takes you to this point from both sides, drives you to this point from both sides. In this case, instead, it's a repeller, so it's an unstable point, because if you just deviate a little bit from this position, the velocity field will take you away from it, both to the right and to the left. This is what I mean. By doing this all the time, you have at least a basic idea of how your motion is going to unfold, which is the minimum information you want to get without solving the without making this extra effort of solving the equations either analytically or numerically with a computer. But I ask you at least, I mean, as often as you can, if you have time and so on, also to solve the equations with a computer, even if I don't ask you to do so, because then it's the best way to see that your forecast is correct. So we draw the graph of f of x. We will be doing this all the time, also, of course, at higher dimensions. We draw the graph of f of x. We identify the fixed points, and we classify the fixed points, distinguishing them in stable and unstable. That's what we did in the case before. That's what we'll be doing all the time. So the fixed points are equilibrium solutions. Stable equilibrium means that the effect of small perturbations vanishes in time. So if you perturb the system a little bit from here, then after a sufficiently long time, the point will return to the equilibrium position, so the perturbation will disappear. There will be no perturbation. Instead, in this case, a small perturbation will increase very fast in time. This is another nonlinear system, of course, because of this x square. And we do the same thing. So the fixed points are the points at which the function to the right becomes 0. So there is 0 velocity. In this case, there are two solutions because it's a quadratic equation, plus and minus 1. This is the vector velocity field. So it's a parabola, of course. It's a second order. It's a quadratic equation, so it's a parabolic function. The vertex is here on the y-axis. And these are the 2 points that I found, plus 1 and minus 1. Whereas this is an attractor. For the same reason, the velocity field is converging to that. I mean, it's driving the system towards that point. And this is a repeller. This is now a concrete example from, life somehow. Electronic circuits, electric circuits. This is a battery, directed current battery with voltage V0. This is my resistor where the current flows. And this is a capacitor, which will accumulate charges of opposite signs on the two sides of it. So, of course, there cannot be any creation or destruction of electric charges. So the sum of the voltage in each of these three components of the circuit should be 0. These are the Kirchhoff's equations, right? So they are engineers. So this is the voltage of the battery minus V0. This is the voltage along the resistor, which is the resistance times the current, I. And this is the voltage on the two sides of the capacitor, which is the charge divided by the capacity C of the capacitor. Now, the current, of course, is the variation of the charge, because it tells you that there is a flow of charges from one side to the other one. So if instead of I here, I put Q dot, I get this. So B0, R, and C are constants. And I can make explicit the function of Q dot here. This is actually a linear system here. Right? So this is not even a nonlinear system. It's very simple, so it's a kind of exponential behavior, like in this case, right? But we can treat it the same way. Linear or nonlinear, we can treat it the same way. So we can ask, for instance, what is the fixed point of this? The fixed point is the point where Q dot is equal to 0. So by solving this thing equal to 0, I get this thing here. So that Q star, the fixed point, is C dot V0. This is a simple line, straight line. That's why the system is linear, because the function, the velocity field is a linear function, it's a straight line. So there is really nothing complicated with that. It has in one intersection, this would be the fixed point, with the x-axis, and this point is an attractor. So it's a stable fixed point, because as you see, the velocity is positive to the left and negative to the right. So it drives the system towards the equilibrium position, which is reached asymptotically. In fact, you can solve analytically this equation and see that you have an exponential approach to this point. In this case, the fixed point is globally stable, whereas usually you have locally stable fixed points, because you can perturb the system. You can kick the system as violently as you want, push him as far as you want from this point, and the system will return back to it. This will happen because there are no other fixed points. In an example like the ones that you've seen here, these are locally stable, because even if this point is stable locally, by changing a little bit, if I kick him past this other point, right, if I perturb the system so drastically that I kick him all the way to this point, he will never return back to this, because he will be repelled by this point here. So these would be locally stable points. In most of the cases, if you have more than one fixed point, they are indeed locally stable. Whereas, in this case, the point is globally stable, because there is only one, essentially. So there is no chance that it will be perturbed by affected by other points. Third example, another nonlinear system because of this cosinus here. So solving the equation means, in this case, asking for which values of x is equal to cosinus of x. This is not an equation that you can solve. You know, it's one of those equations when you mix, for instance, the x with exponential and so on. Those are equations that you cannot solve. You can solve them only numerically. But there are tricks to do that, at least to have a qualitative sense of the solution. This is y equal to x. It's a straight line. It's a bisector of the first and the third quadrant. This is cosinus of x. I'm looking for the intersection of these two lines, because this would be the value of x dot, x star, where these two functions coincide. This would be the geometric solution of this equation here that I cannot solve analytically. So there is only one solution, because the two curves here cross on only one line. You see, this is the cosinus, is periodic, this is a straight line, they only cross here. So there is only one fixed point. What kind of fixed point is that? This is stable or unstable? Now, by looking at this one, you see that when x is bigger than cosinus of x, then the velocity is positive. When x means, in this case, so when this function, the straight line, is above the cosinus, then this difference is positive, and the velocity is positive. So you see, to the right of this, the line here is above cosinus. So here the velocity is positive, whereas here is negative. So this point is unstable, because the velocity would take the system away from it if you perturb the system a little bit. If you kick him a little off its equilibrium position. So these graphical methods will be used frequently during this course, sometimes, to solve equations like this, which do not have an analytic solution. Okay, so this is what... another example, actually a very famous example from population biology, is the logistic growth. So population growth, the simplest model is this, so that the population grows at a rate which is linearly, so which is proportional to the population itself. This is nothing but this equation here with a coefficient, which is r, the rate of change. Now, if this is the real equation regulating the growth of population, we'll be in big trouble, right? Because the solution will be this. So population will grow exponentially in time, up to the point that there will be no more resources to feed the whole population. This is what happens for some species of bacteria, for instance. At constant temperature, in the absence of predators, and if there is enough food to sustain the growth. But this is not realistic. I mean, it cannot last forever, obviously. Because this is what we get. So we get billions of individuals and so on. Actually, the more people will be there, the faster, I mean, they will reproduce because of this. So an alternative, a more realistic alternative, is to set a decrease in behavior for the growth rate. The growth rate is basically the ratio between the derivative of n and n. So before, this ratio is just r, and is a constant. This is what creates the trouble, because it means that even if the population is very big, the relative rate of growth is the same, so the system grows exponentially, which is what we don't want. We know that it's not true in real systems, except for some limited phases. What we want is that if the population becomes big enough, at some point this R goes to 0. So we want to set a limit somehow, or a natural size, which is called carrying capacity, for the largest population that can live in a given environment with a given amount of resources for a long time without getting extinct, without fighting for survival and killing each other. See? The simplest, of course, way to implement this is just to have a linear dependence of R on n. That's the simplest as usual. No? A linear thing is the simplest thing. So if n dot divided by n is a linear, because you see once I bring n to the other side, then you have a linear dependence on n, up to the point when n becomes equal to k, and then R becomes 0. So the n dot divided by n becomes 0, which is what I want. So in this case, I'm sure that the growth, the exponential growth, cannot be sustained indefinitely. At some point, the population won't grow anymore. This is analytically solvable. Actually, just there is an n squared thing. So if you want, you can just solve this thing. It's a simple integral. But we want to study it as, with this new geometric approach that I'm trying to teach you here. So this quadratic equation means that there are two fixed points. One is obviously n star equal to 0, because if you put n equal to 0, this is 0. If you put n equal to k, this is also 0. So there are two fixed points. The logistic equation was actually originally introduced by Verhulst in 1838 as a basic model of population, of growth of human population. Although in the 1800s, population was not really growing exponentially, it was growing sufficiently fast. Let's say that for human population, this is not a good model. It's not really a very believable model. So what kind of fixed points do we have here? So there are two. This is the velocity vector, n dot here. You have a square, which is a parabolic function, which is 0 here, it's 0 here, and it has a vertex here at k half. So obviously here the velocity is positive, and here the velocity is negative because it goes down, right? Here is positive because it's above 0, and here is negative because it's below 0. So this point here, n star 2 equal to k, is stable, and this one is unstable. So what does it mean practically thinking about real living beings like bacteria? That if I have, say, a small population of bacteria, then it will grow exponentially initially somehow. But then the growth will be decelerated, and it will converge to this carrying capacity k. If I have many bacteria, many more than k, they will sort of starve. The population will decrease. Again, they will converge to k. The logistic equation is a good equation for very simple beings like bacteria in this condition. Like I say, more or less constant temperature, enough food, and no predators. But if you take more complicated organisms, like even fruit flies, which have eggs, larvae, pupae, more complicated reproduction cycle, then it's shown, so you see it in the data, that you don't really have an exponential growth if you start really from very small population. Indefinitely, so of course, you have an exponential growth, but you don't really have a carrying capacity. You don't really converge to some sort of stable level for the population. There will be oscillations. So you need a more complicated model. But for simple organisms, this is a good model. And in fact, it's a very popular equation that in population biology is very often used. But you see, I know all I need to know. I know that there is, in this case, a carrying capacity. The system will converge. Of course, in this case, I didn't put negative values of n because it doesn't make any sense, right? This is a population. How many individuals I have? So it can only be a positive number or 0. If it's slightly non-zero, then it will grow very fast, and then it will start to decrease until you get k. If it's larger than k, then it will decrease until it reaches k. So the only possible future for this population is to reach a population size of k, the so-called carrying capacity. And depending on where you start, as you've seen also in the case of the sinus before, you get this type of trajectories here. If you start from this is 0, this is k, and this is bigger than k. This is k half. If you start from before k half here, you have first exponential growth, very fast. You see that it's concave up. It's growing very fast. But then when you reach k half, you have an inflection point because here the acceleration is 0 because the velocity now decreases instead of increasing. And then it becomes concave down until it approaches the stable carrying capacity value k. If you start from a point here to the right, so between k half and k, like here, then the velocity is going down monotonically, and then you have this. You don't have any inflection point. You have that the concavity is systematically down from the beginning till the end of the motion. If you are above k here, you see that the population goes down again monotonically and with the same type, with the same sign of the convexity or the concavity, in this case concave up, all the way to the equilibrium position k. So this is what you've seen before for the other function, but this is what you can do all the time. If you see that the velocity is changing its behavior, and at some point it has to change, because in order to go from one fixed point to another one, it must reach a maximum if it's a continuous function, right? At least one maximum. But then, of course, it could be a local maximum, but then there is certainly the curve has to come down, and then you know qualitatively how the motion unfolds. So let's discuss now about linear stability, which is a way to see immediately, without even drawing the vector fields, the velocity fields, whether a given fixed point is stable or unstable. And we do what I told you before. We apply a small perturbation from the equilibrium position x dot, x star, and you call eta t this perturbation. So we start basically from a point xt, which is very close to x star, and we see how this difference changes in time. If it shrinks to 0, then it's a stable point. If it grows, instead, it's an unstable point. So in order to find out how it changes in time, we have to make the derivative of this. X star is a constant, so the derivative of eta is just the derivative of x, which is f of x, where x is, as I said, x star plus eta. All right? But now, if eta is small, sufficiently small with respect to x star, I can make a Fourier Taylor expansion of this thing and stop at the first, after the first order approximation. So I have, of course, if eta is sufficiently small, I have f x star plus eta times the derivative of x of f at the point x star plus terms of quadratic or cubic order, quartic order, and so on, that I can forget if eta is small enough. But of course, since x star is a fixed point by construction, because I'm moving from a fixed point, then of course the velocity is 0 at that point. So this term is 0 by construction, because I'm moving away from a fixed point. So what do I get then? That eta star, which is equal to that, is just equal to eta times this derivative plus terms of the order of eta square or higher, which I can forget about. So approximately, if this perturbation is sufficiently small, the derivative of the perturbation, so the velocity of the perturbation, is proportional to the perturbation itself times this constant here, this derivative, which is exactly this equation here. You see, eta dot proportional, you can equal, say, eta times a constant, which gives exponential behavior. Only, what type of exponential? If it's decreasing exponential, increasing exponential, depends on the sign of this coefficient. If f prime here is negative, if it's positive, then of course it's just like in this case, you have exponential growth. So the point would be driven away from the from the fixed point. If it's negative, instead you have decreasing exponential, so the perturbation will die. Okay? This is what. So basically, what does this tell you? That by checking the sign of the derivative, or the first derivative of f in each of the fixed points, you can predict whether it is an attractive fixed point, so stable, or a repulsive fixed point, unstable. Just by this, without even checking the diagram that I showed you so far. Of course, all these things match, they fit with each other, but this is a quick and dirty way to find out. Of course, it can also happen, and I will show you a few examples, that this derivative is 0. If it's 0, there is nothing you can tell, because that means that this, if this is 0, the second order terms and higher are the ones that count. So anything can happen, and we're going to see then examples of this. But if there is a sign, then you can be sure that if it's positive, it's an unstable point. If it's negative, it is a stable point. In fact, since this thing, by solving this equation, this is a constant, right? It's a number. This tells you basically how fast this exponential progresses in time, towards 0 or towards infinity. So so the inverse of this, so by solving this equation, so by solving this, if you have a lambda here, you have e to the t divided by lambda. This is what you get by solving this equation. So where lambda in this case is this f, lambda is this f, so first derivative of the velocity field f at a fixed point. So this tells you basically how quickly the exponential progresses in time. So it is a characteristic scale, time scale of the motion. Because you know that when t is much bigger than this number, then the exponential, of course, will kill or will blow up the number, depending on the sign of this, if it's positive or negative. So you know quite a lot from this very simple number here. Okay? There are questions about this? You can ask me anything, of course. So, please? Yeah.
About the book.
Oh, yeah.
Library copies, or is it good to order from Amazon or vice?
No, you find it online.
Okay, that makes sense.
So, yeah, it's much easier, right? So you can just go through that, and of course the slides are there too. But yeah, if you want to know more, and of course there are more exercises, then I can give you. It's already there. In fact, perhaps I should make it somehow password restricted, the access to that, because we didn't really buy it. So it's a way somehow to make your life easier. Then you find everything there, because I'm just using this book, and of course sometimes I pick something from other places, but usually I'm just following this mostly. So you can find this very easily. So linear stability, okay? So you take, if you have a vector field, velocity field f of x, you find the zeros, the values of x at which this is 0, and you compute the first derivative at each of these values. If it's positive, the point there is a repeller. It's an unstable fixed point. If it's negative, instead it's a stable fixed point, also called an attractor, because the motion will be attracted to that. And this is an example. This is the same example that we considered at the beginning with the sinus. We know everything about the system now, I mean qualitatively at least. So first I find the zeros, which are the values at which the sinus is 0. So 0, pi, 2 pi, 3 pi, and also minus pi, minus 2 pi, minus 3 pi. The function is periodical. Periodic. So the derivative of sinus is cosinus, right? So the cosinus computed for the fixed points give you, of course, 1 or minus 1. So when h is even, 0, 2 pi, 4 pi, 6 pi, and so on, you have plus 1. When it is odd, minus pi or minus 3 pi, plus 5 pi, and so on is minus 1. So based on what I told you before, since in this case the derivative of f at the fixed points is non-zero, then I know exactly how to classify the fixed points. which are unstable if k is even, where k actually should be h. So this is a mistake here. Unstable if h is even, stable if h is odd, would be this thing here. I could have called it k. So yeah, I should put it. So k is even, like 2 pi, unstable. You see, here there is an empty circle, it's unstable. Here the circle is full. This is actually the way to indicate. Full circle, so black dot, stable point, white dot, unstable point. This is the convention. And you see that all of this is satisfied here. But we knew it because we just proved it that this is the case. In the example of the logistic equation that we've seen before, for the population growth, there are 2 fixed points, 0, and the carrying capacity k. The derivative of the velocity field is this. If n star is 0, this goes away, and this is r, which is positive. So it's an unstable point. If I put instead k, k divided by k is 1, so r minus 2r is minus r, which is negative. So the point is stable, which is what we knew already from before by drawing the velocity field. But I found this without drawing the velocity field. So I somehow saved one step. I didn't need to make this thing after computing that. I already knew what kind of fixed point I had. Now, what happens instead if f prime is exactly 0? So then this linear stability analysis is worthless. It cannot help us in any way, and everything can happen, like is shown in these examples here. These 4 examples that we're going to discuss separately in the next slide. And this is the last thing I can tell you today, I'm afraid. So here you have a cubic with a minus, cubic with a plus, square, and then 0. What happens in these cases? X star equal to 0. Of course, I mean, the fixed point is 0 here, because this is the only value where this thing is 0. The same here, the same here, right? What kind of fixed points are they? So for A, B, and C, x star equal to 0 is the only fixed point that you have. But what type of fixed point it is? Is that, sorry. If I make a derivative of this, then I find minus 3 times x squared. Here I have 3 times x squared. Here I have 2 times x. In all these cases, the derivative is 0 at a fixed point. So the linear stability analysis does not help me at all. In this case, actually, all the points are fixed points. Because you see, basically, this is telling you that the velocity of the system is 0 always. So wherever you are, the point doesn't move. So the whole line is full of equilibrium position, as you see here. In this case, they are separated to show them, but of course, it's an infinite. Any point is good, right? So there is a continuous distribution of values. So all the values of x are good for equilibrium positions. But in the other 3 cases, you see this is the first cubic, this is the second cubic, this is the parabola. Anything can happen. In this case, for instance, the point is stable, because you see the velocity is positive here, negative here, so converges to the point. In this case, this is unstable for the opposite reason. I just changed the sign here. In this case, it's very rare. It is called half stable because you see, in fact, that's the reason why it's half black and half white. Because if you're here, of course, you don't move. But if you move to the left a little bit, then the velocity field will take you back to the point. If you go to the right a little bit instead, the velocity field will take you away. So it is stable if you go to one side, and it's unstable if you go to the other side. That's why it's called half stable. Please?
Yes, it makes sense because if you lower the parabola, you have 2 points.
Yes, this is a bifurcation, yes. Yeah, and that's exactly what you're going to see. That's what you're going to see next time with the bifurcation, when you can change with the parameter the whole distribution of fixed points. Yeah. Whereas here instead, you see all the points are fixed points, all of them. Any point on the x-axis is a fixed point because the velocity is systematically 0. Unstable here, half stable, line of fixed points. Okay, so this is probably really the very last thing that I can tell you. Just to make sure that we know this, we are aware of this. Because this is a tool, this is a fundamental result in all these differential equations, and also, of course, for mechanics. But it's a very useful tool for us to understand sometimes where to draw our trajectories. And I'll tell you why. Suppose that I have this equation here. It's nonlinear because you see x is to the power 1/3, which is not 1. And in principle, it has a fixed point at x equal to 0. No? So I want to know what is the future evolution of the motion of this, for this system. If I start from 0, okay? Well, if I start from 0, actually it should be stable all the time, right? It's not so simple here, however. So the trivial solution is, of course, the point doesn't move, right? It's a stable fixed point, sort of. I didn't say anything about stability here, but it's a fixed point. So if I'm there, I will never leave the place. This is what you can infer from what I told you so far today. But in this specific case, there is another solution, which is this. You can just integrate the equation. It's very simple, and you get this. This is also a solution of this thing starting from 0, because when t is equal to 0, it's also 0. So what does this teach us? That I found, for the very same system, starting at the very same initial condition, two solutions of motion, for the equation of motion. This is bad. It means somehow I cannot really make a prediction if I have many possibilities. Actually, and this is funny, there are infinite solutions to this equation of motion with this initial condition. Because I can stay at 0 up to some time t0 that I fix arbitrary, and starting from t0, I move like this. So I can, by changing t0, I can get then any possible solutions, any infinite number of solutions. So how is it possible that the same equation with the very same initial condition gives infinite solutions? We don't like that. This is a pathology. And we'll try in the future of this course, and fortunately in many cases this is what happens, to avoid this pathology. But let's try to understand where it comes from. So there are infinitely many solutions by combining the two solutions that I showed you before. You can really show it. But without uniqueness, this whole geometric business that I told you fails, doesn't take us anywhere. So we should try to avoid, like, the plug, this kind of scenario. Where does the non-uniqueness come from? Suppose that I take, remember, I can make a derivative of this. If I make a derivative of this, I get this thing here, which is a negative exponent here. If I compute this derivative when x star is equal to 0, I get infinite. Because, as you can see here, this is the profile of the velocity field. The tangent, because the derivative of this is just a tangent, is vertical. You see it here. The tangent at the origin here is vertical. So it is super unstable, so to speak. It's this type of divergences which creates trouble, and we should avoid, like I say, like the plug. So we should make sure that we don't have this situation. We don't have situations in which the derivative of the field diverges. And this is, in fact, one of the conditions of the existence and uniqueness theorem, which says more or less this. I have this equation here to solve this system with this initial condition. If f of x and its derivative are continuous on an open interval r on the x-axis, open interval means that if this is the x-axis, so say this is lambda minus lambda, lambda, so to speak, but it can be anything, and the extremes are not included, and x0 is a point of this interval. If f of x and its derivative are continuous within this, then it's possible to show that there is one solution to this problem here with this initial condition, and only one solution within an interval from minus tau to tau, where 0 is, of course, the initial point. So basically, it's possible to construct a solution a little far in the future from the initial point, and also a little back to the past from the initial point, because in the case of Newtonian mechanics, the future and the past are the same thing. Somehow you can predict them with equal accuracy. So there is a symmetry. This is what the existence and uniqueness theorem says. So if f of x is smooth enough, solutions exist and they are unique. Okay? So why did we get infinite solutions the case before? Because f prime of x was not continuous there. It was diverging at a point of the interval that you are interested in. And then you can create this kind of mess. But you can be sure, because this is a theorem, it's not a speculation, that instead if f of x and f prime of x are continuous, they are sufficiently well behaved. For the layman, this is the cheap version. So if fx is smooth enough, solutions exist and are unique. Okay, so remember this at least, for the rest of the week, at least. However, the theorem says the solution exists for a limited interval. It's not guaranteed to exist forever. And this is an example that shows you that. It looks very simple system. It's nonlinear because x is square, of course. So the function, there is a quadratic dependence on x, which is nonlinear, starting from a point x0. The function, the velocity field is f of x, which is this very simple parabola, which is of course continuous. Actually, it's continuous with all its derivative, because I can derive it forever. At some point I get 0, and then I keep having 0. It's always continuous. And all its derivatives are actually in all the range of x values, from minus infinity to plus infinity. So it's not even confined to a range. It's really continuous everywhere. So the theorem applies. If I start from any point, I should be able to construct one and only one solution of this problem. But for a limited time. Because actually, in this case, I can solve exactly this equation. I can show you that the solution cannot exist for any time. If I solve this equation here by separating the variables as usually, I get that x of t is equal to the tangents of t. And as you know, if I start my motion at t equal to 0, the tangents is not defined at pi half and minus pi half because it diverges there, right? So the motion, if you start from 0, can only go to the future up to pi half and to the past up to minus pi half. There is nothing beyond that. So then the particle will just disappear. Actually, it's very interesting that this is an example, a rare example of a motion which takes the point to infinity in a finite time. So after pi half, basically, the particle is shift forever. So it's a big kick. And in fact, this is called blow up. And it's a type of mechanism which is common to explosive things, like combustion, for instance, in the engines of cars. These are processes that unfold according to dynamics of this kind, in which in a very short time you have a huge change in the dynamics of the system. So this is a typical example. So the solution exists in a finite interval, but not forever, because things like this can happen. At some point, the thing is not definite. Actually, this is, we were supposed to do the exercises today. Perhaps you didn't know that there was an exercise today, so I can still use a few minutes then to finish where I wanted, because the course is short enough, and I don't think I will be needing more than 10 minutes. One of the things that I always remember from this course, because then of course I had to go through that to prepare for the lectures and so on, but there are things that you never forget. Hopefully it will happen to you too. In one dimension, so if you make motions on a line, like in these cases, there are no oscillations. It's not possible to have periodic motion, like oscillating behavior to the right and the left. I'm going to show that. In 2 dimensions, there may be oscillations, like for instance the harmonic oscillator. It's a classic case. It's a second-order system, so 2-dimensional system, which oscillates, but there is no chaos. In 3 and higher dimension, there can be also chaos. Okay, so first, on the line, there are no oscillations. On the plane, there is no chaos. In 3 and higher dimensions, there is chaos. Okay, anyway, so why is there no oscillations? You can see it already from here. So what we've seen, I mean, since this is a generic situation, I have a vector, a velocity field, which is represented by this curve here, and at some point it may cross the horizontal axis. The crossing points are the fixed points, because it's where the velocity is 0. We've seen, actually, the way these points are approached in the motion asymptotically. It never happens that the point, for instance, here, moving to the right, overshoots the point, going over the point itself, and then comes back, doing an oscillation. It never really happens because at each of this point, the velocity can only have one sign. because we are on the line. F of x is a well-defined function, so it gives you only one value at each point. If you are in 2 and higher dimension, this instead does not happen because you may have, since you have a whole plane, as you're going to see, then you can have also, so the velocity has 2 components, and then you can have oscillations. But in this case, velocity has only one component. It can be positive or negative, and in order for f to be well behaved, it can be only positive or only negative, or at post 0 at any given point on the x-axis. So there cannot be oscillations, because it never happens that oscillation means that at some point you have to return to the same position, right? So at each point of the range where the oscillation takes place, the velocity has to have one sign and at the same time also the other sign. Otherwise, there is no oscillation, right, like in a pendulum. But the pendulum is a second-order system, so it has 2 variables because it's a second-order equation. It's a Newton equation, which becomes a first-order equation. It's a second-order system, which becomes a first-order system with 2 variables if I make the trick of using the velocity as auxiliary variable, as we're going to do in the future. So this is why there are no oscillations. It can be proven in many other ways. One way to do it is with potentials. So if I have a function like this, and f is behaved, this is a continuous function with its derivative and everything, I can make the integral of a continuous function, which is the potential. So there must exist a function v of x, which is called the potential, such that the derivative of v of x with respect to x with a change, with the sign change here, is exactly f of x. We know this is a basic assumption about the integral. Any continuous function can be integrated. Okay? So why would I do that? Why would I care about this? So if I make the derivative of this function with respect to time this time, so I want to see how this function called the potential changes in time during the motion. So this is the derivative, but I can use a chain of derivative because these are all functions of a single variable, which is x for v, but x is a dependent variable of t, which is the independent variable. So this is a chain of derivatives, classic things in calculus, but the x in the t, which is the velocity x dot, is exactly f of x, which is minus the v divided, so the derivative of v with respect to x. So I get minus the square of this derivative, which is obviously, we cannot be positive. It can be negative or 0 because of this thing. It's a square, and there is a minus sign here. So this very simple line tells us that if I compute the potential of any system of this kind by integrating the function f and changing the sign, the potential will not increase during the motion because the derivative will never be positive. Okay? So the potential will always go either to a lower value during the trajectory, it will keep decreasing, or it will stay stable. It can never grow. So the particle always moves towards a lower potential. And I think that as a physicist or somebody in basic physics courses, you've seen, with the potential that you have this maxima and this minima, and usually the particle converge to the minimum of the potential, right? As if they are rolling there. So this is what I showed you before. Of course, if you have a fixed point, fx is 0. Fx is 0 means that the derivative, this derivative here is 0, because this is exactly fx. So this is 0 too. So of course, the potential doesn't change there, doesn't need to change there. And the particle stays there forever. So the potential stays constant in time only at equilibrium points, only at the fixed points, because only in that case this thing is 0 because of this, right, by construction. So equilibrium points correspond to values where the derivative of the potential is 0. So a function whose derivative is 0 is at an extremum, either a maximum or a minimum. So the fixed points of any system of this kind, any dynamic system in this kind, correspond to extrema in the potential of the corresponding to the system, either maxima or minima. So if it's a minimum of v, it means that the second derivative is positive. This is calculus, so I don't need to teach you that. The minimum is the point at which the first derivative is 0 and the second is positive. And the but the second derivative of this is the first derivative of f, or x of f, sorry. Since there is a minus sign, because I showed you before, sorry, is here, right? Since there is a minus sign, this positive means that this is negative. And we've seen before from the linear stability analysis that if I am at a fixed point whose first derivative of f is negative, this is a stable fixed point. Otherwise, it's unstable. So stable fixed points correspond to minima of v. Unstable fixed points correspond to maxima of v. Let's take a look in a concrete example. So this actually is a linear system. This is a usual exponential thing. We've seen it already. We see it all the time. So finding the potential means solving this equation. I have to find the function whose derivative is, with a minus sign, is equals the function, the vector velocity field f, which in this case is minus x. Solving this equation means that the potential is this. Of course, since it's an integral, there is an additive constant that I can fix as I like. It doesn't really change anything. I can fix it to 0, this c here. And it's usually what is done. I don't need to, I can always change it as I like, but it's a constant, doesn't change anything. So this would be the potential for this system here. The fixed points then correspond to the maxima and to the minima of this function. This function has only one minimum, and there is no maximum. So it has one fixed point, and it is stable, because it's a minimum of v. And we know that because this thing corresponds to a decreasing exponential, because it would be this. Decreasing exponential is a function that then will go to 0. So 0 is a fixed point, and it is stable because the system will converge exponentially to it. So we knew that, but this is another way to see it, using potentials. They can be useful sometimes to see things right away. Another example is this little more complicated function. Now this is a nonlinear system. And again, I have to solve this. That gives me this quartic equation with an arbitrary constant that I can set to 0, because I can fix any value for it. And this is what it looks like. This would be this function here. So in this case, it's not so simple. There is one maximum here at 0 and two minima here. They actually, because of the symmetry of the system, have exactly the same height. So there are 3 fixed points. This is unstable. These are stable. You can find the same results by analyzing fx directly as we've done before. This is a cubic. It has 3 solutions. One is x equal to 0, as you can see here. The other 2 are plus and minus 1. So this is easy to see by drawing the velocity field or by computing the derivative of f at those points, that the 2 points at plus and minus 1 are stable fixed points, and the one at the origin is 0. It's an unstable fixed point. Okay, guys, that was the last thing. Despite the accent, we managed to carry it through. This is what I would like you to do next week, and you find it on a separate PDF. I mean, just this one slide to make sure that you find it. Otherwise, it's the last slide of this lecture slides of today. 3 types of exercises. You have, of course, only one-dimensional system, very simple. You have to sketch the vector field on the real line, as I showed you. basically to see where it is positive, in which ranges of x is positive, where it is negative, where it is 0, which would be the fixed points, and whether these fixed points are stable or unstable. By going through the slides, if you don't remember it from what I told you now, you should have enough information to classify fixed points. You can do it visually, you can do it with a stability analysis by computing the derivative of f at the fixed points and checking the sign. If the derivative of f, which would be this is f, right? This is whatever is the right. So the derivative of this at the fixed points is positive, then the point is unstable. If it's negative, it is stable. Or you can use the potential. You can do it whatever you want. The more, the better for you. Means it's just a way to show that you understood. And here, instead, you are invited to use the linear stability analysis. So basically, again, to make really, in this case, the derivative of these functions here at the fixed points, and based on their sign, to conclude whether this fixed point is stable or unstable. How many there are, and if they are stable or unstable by computing the derivative. And the last thing instead is about the use of the potential. You have to derive the potential for these two functions here, for these two systems, and based on their maxima and minima, as I showed you before, then identify the fixed points and classify their stability. That's all. So if there are questions, I mean, either now, of course, or you can come to my office, you can send me emails. I'd be glad to do that. And if there are problems in solving these exercises, I mean, we should discuss this, you know, in the exercise session next week at the end of the class right here for those who want to stay. If you are just 2 or 3, we can just go having lunch and discuss the things so, you know, on the table. We don't need to stay here then. It depends. Okay, guys, so that would be all. And yeah, if there is no other questions, or if there is a question about, you know, material and so on, since it's the first time that we meet, please ask me. That, if you want to get another chocolate, you know, we can always agree on these things. Otherwise, see you next Wednesday.